voltage is or gets connected to the metal housing, then there will be a short to earth, and the fuse will just blow off, and then you're safe. So that's the main reason. Okay, so this is the earth connection. In the examples that, or in the first example we looked at with battery, and this is typical for battery-driven devices, there's of course no earth connection. But still in those systems, you usually pick one node as the reference node and say this is 0 volt. And if you want to show that in a diagram, in a circuit diagram, then you can use, for instance, this symbol here or this symbol here. The one on the right is not a standard symbol, but it's widely used. That's why I'm showing it here. And you will also find it on our slides. So these are symbols that characterize reference nodes that are not earth connected. Okay, now on the left, in the lower left part of the slide, I'm showing a circuit diagram that doesn't seem to show a circuit, because there are no visible connections down here and down here. But I tell you, it's still the same circuit compared to the one above. Why? Because you can make connections or describe connections in such a diagram without drawing lines. Connect by name is what we call it. You see that here at this node, I said the voltage at this node should be VQ. And on the left side, you see that the voltage at this node is also VQ. It's the same voltage, and this tells you that there must be a connection between those two. And the same thing down here. This node is earth connected, this one is too. So there is a connection between those two nodes. So you don't see the connections, but you should know that they are there. And we very often do that, especially for ground connections and supply connections, because if you draw all those wires in a complex system, you have to draw a lot. You can make it just more simple and make the diagram look more nice.
So can you repeat? Didn't understand.
Pardon?
Didn't understand. Can you repeat?
Okay, which part you didn't understand? Everything.
No, you say no, sir, everything not.
Okay, up here. So I just explained it again. There was a question in the room. In the upper diagram, we show by using a line that there is an electric connection from this node to this node. Yes.
Okay. For simplicity, we do the second diagram, right?
Exactly.
There should be a connection.
In reality, there is a wire. Otherwise, you wouldn't have VQ on the right side there. Yeah. Okay. Any more questions up to here? No? Cool. Then let's talk about resistance. I showed the symbol before. The symbol is just looking like this. It's very simple. It's a rectangle with two connectors. And this denotes a resistor device. And what is a resistor device? I defined it as a component that resists the current, which means that if I try to push a current through a resistor, it's harder when the resistance value is higher. How can I push a current through a resistor? Well, I connect the voltage to the two terminals of the resistor. A current will flow as a reaction to that. For one given voltage, the current will be higher when the resistor value is lower. And Mr. Ohm, Georg Simon Ohm, find out that for many materials, there is a proportionality, or you can observe a proportionality between voltage and current. And the proportionality constant is the resistance, R. R is the common symbol for that. The resistance has its own unit, which is ohm. We use an omega. We do not write ohm usually. We use an omega. And it is, of course, derived from volt and amps. When you solve this equation for R, then you have R is equal to V over I. So that's voltage over current. V volt over amps. So that's Ohm's law. Very fundamental. Who has not heard about Ohm's law before? Nobody. Okay. That's good. Who has not heard about the conductance? Not the resistance, but the conductance. You know all what the conductance is? Yeah? You know it. Okay, thank you. Well, the conductance, you see it on the right here.
Are you I equal to A? How?
Pardon?
I equal to A.
I equal to
A.
A.
It's the units bracket. I is the current, and the unit of the current is the amps. That's the A.
Oh, you're looking at this here. Oh, have I explained it last time? I think
Yeah.
I did, right? So this is how you read it again. When you see these kinds of brackets here, you read it as the unit of V is.
But this is unit.
The unit of V is. It's a standard kind of writing this down. Unit of V is volt, unit of I is amps. Yeah? Okay. Now the conductance. The conductance is simply 1 over R. So to be honest with you, we wouldn't really need this G, right? We could do everything with just the resistance. G is 1 over R. But anyways, G is very common because sometimes, especially when you talk about things, it's nicer to talk about how well something is conducting as opposed to how bad something is conducting. Like a higher resistance says it's not conducting very well. A higher conductance says it's conducting very well. And also some mathematical equations when you analyze circuits are sometimes nicer to write down when you use the G instead of the R. We will see a few examples of that. Most times we will use just the resistance. But in some cases we will also use the conductance. The conductance even has its own unit. The unit of G is Siemens, the big S. Yeah.
So if you have a battery and just a wire that loops around, doesn't that cause a problem? Because if you don't have a resistor on that wire, you technically have infinite conductance.
Exactly, it is a problem. I don't know if everybody heard this at home. The question was, if you just have a battery and you connect the two poles with just a wire, is that a problem? Because there's no current limiting resistance in that circuit. Well, there are two aspects. There is some resistance in the circuit because the wire is never an ideal conductor. The wire itself has some resistance. So what I wrote down up here, the resistor is a component that resists the current, is basically a special case. I describe the resistance as a device, really. But in fact, resistance is a material property. And metal conductors have some amount of resistance. Any wire has some amount of resistance. And now the second aspect of your question, is it a problem? Yes, it is a problem because this resistance will be low. The current will be very high. That's what Ohm's law tells us. I should not recommend you trying it, but
once I had tried my hand.
You burned your fingers?
Yeah.
It becomes hot, right? Because the current becomes so high. And in the worst case, even the battery may just blow up. So when you do this with the normal standard little 1.5 volt batteries that everybody knows, it may not be that bad. They become hot and it takes some while. If you realize it early enough, maybe nothing happens really, but I wouldn't try it anyways. But if you do it with a lithium polymer accu, let's say from a remote controlled car or something, they have really high performance accumulators in there, and you do a short circuit or create a short circuit, I think you have a good chance to burn them. So be careful with that. A short circuit is never a good idea. Okay, but this brings us or leads us directly to my next point. I just said the resistance, when it's a device, it's really a special case. And many other things have the property of resistance in them, like the wires or the light bulb that we have looked at in our previous examples. This little filament in the light bulb, of course, has a resistance. And at least when the light bulb lights up, when it's glowing, then it's a pretty high resistance. So there's also temperature dependence. When it gets hot, resistance may be higher compared to when it's cold. We will talk about that later on, not today, but maybe on Friday or next week. A motor has an inner resistance because there's a huge coil, kind of a transformer in there, or even several coils, and a coil is a long, long wire. This wire has a resistance. Any connection has a resistance, but when we draw a circuit diagram like this one here on this slide, when we draw it like this, then we indicate that we are not really interested in the wire resistance, although the real wires have one. As long as we don't have a good reason for taking the wire resistance into account, we do not show it in the diagram, and we do not take it into account in our calculations in the circuit analysis. If the effect of the wire resistance is significant, then we should probably just indicate the wire resistance in the circuit diagram. We could just add a resistance symbol there and say that it's like RL. No, RW. In German, I always say RL, Leitung, but in English, it would be a wire, RW. Yeah. I mean, the idea behind these simplified diagrams is always that we only show what we're interested in, only the relevant things. If these parasitic effects become relevant, we have to show them. And we have to take them into account in any calculations. Now, in our second example, the lamp connected to the public network, we also talked about, or we also saw a switch. And I've shown to you the symbol for an open switch and a closed switch. Switches are also a very good example for devices that ideally don't have any resistance. but in reality they have. I mean, if the switch is open, of course, the resistance should be infinite. There should be no current. But if the switch is closed and it's conducting, there should ideally be no resistance. But in fact, the resistance of switches is even larger. It's more severe. It's more important than switches of wires, than resistances of wires. Especially when you use the switch or when you have used the switch for a long time. Like the normal light switches on the walls. When you use them over years, and you later on you just open them up and take them apart, you will probably see that the contacts don't look very fresh anymore. Like every time you open the switch, in the very first moment, you will see a little spark between the two contacts here at this point. When they are really close but not connected anymore, there will be a spark. It's like lightning. And this, over years, just burns the contacts. I have even had a switch on the wall at home that wouldn't open anymore because the two contacts just burned together. So this can also happen. Another example, many years ago, I owned a motorcycle, and who's driving a motorcycle? Only one person. So what are you doing in winter?
Don't drive.
Don't drive.
Because in my country, it doesn't matter.
So you don't drive, you disconnect the battery probably?
No.
You don't?
No.
Okay.
I mean, yeah. Turn the light.
Pardon?
Every day you have to start the light.
Oh, you start it every day? Okay.
Otherwise, the battery will be low. It also doesn't matter. Like in Germany, it may be a problem, but in my country, it doesn't matter. Yeah,
because it's warmer.
Yeah.
Okay.
In our country, there is no winter. It's summer and.
Okay, bad question. Good, forget it. Well, what I did was always every winter I took the battery out. I put the motorcycle in the garage so that it's dry and not too cold. I charged the battery up, put it into my basement and all that. And then in spring, I take the battery out, put it in the motorcycle, and hopefully, after recharging it once more, hopefully it starts.
That makes sense.
Yeah, it always worked out, except for 1 year. Nothing happened. I turned the key. I saw all the instruments lighting up. Everything seemed fine. And then I pushed the starter and everything was dark. And I heard nothing. And it took me a day to find out what the problem was. And it's exactly what I explained to you here. Like, it was not a very modern motorcycle. It was kind of older already. And I don't know if you know these glass fuses. Little glass tubes like this with contacts on both sides here. And then you have kind of metal clamps where you push the fuse in. And these metal contacts here between fuse and the clamps, there was so much corrosion that it was a very high resistance at this point. And all the voltage that came from the battery was now here. And there was no voltage left for the starter. No voltage left for the lighter, for the lights and the instruments. So that's the reason why everything became dark. This resistance was dominant. All the other resistances in the circuit were just negligible. And how did I find out? Well, after trying hours and hours, starting again, the plastic at the bottom just melted because this became so hot. We had all the power at this point. The plastic melted. This was the reason. Everything else seemed to be fine. So this is exactly the issue that I explained to you here. Parasitic resistances of wires, of any kind of contact, any plugs, switches, everything basically has some resistances. This may also change over time. When you go to the lab in the second semester, you may also see these effects. You will build circuits, or some of the circuits, on this type of breadboard. You plug in wires, you plug in devices into these components here. And of course, many students use these breadboards. They use them for years. So they are not all perfect anymore. So sometimes you see very strange effects when you build your circuits, and then you have to find out what the problem is. And every couple of years, you even have to buy new ones because they are just, this doesn't look that good anymore. It's like melted. Okay, good. So resistance is not really just only a device, it is also a material property. Keep that in mind. When did we start? At 10, right?
Yeah.
Yeah. Okay. It's a good time to take a break, 5 minutes. I'll be back at about 10:47, 48, something like that.